So, welcome back to this problem solving session for the NPTEL course Foundation Engineering. So, currently we are in week 10, and in the last week we started solving a few problems regarding this retaining wall or lateral earth pressure theories. Okay, so first we'll have a quick recap for the topics which we have learned from this week. And as you know that in the last week we mostly discussed about the calculation of lateral earth pressure based on Rankine's earth pressure theory. So Rankine basically presumed or assumed some conditions to derive the earth pressure theories. So and one of those assumptions is that he didn't consider any angle or angle of friction in between the wall surface, the back face of the wall, and the backfill material. Okay, so if this is the retaining wall, so this is the backfill surface which I am talking about, and as you know, this is the backfill material or backfill. Now at the interface, that is along the surface of the, sorry, this is not backfill surface, this is called the retaining wall backface, okay, sorry, this is the wall backface. So in the Rankine's theory, no angle of friction, wall friction, that is in between the wall backface and the backfill material is considered. Again, this wall backface is considered to be perpendicular, okay, or vertical. Whereas in this theory, there is one more theory to determine the lateral earth pressure, which is called Coulomb's theory of earth pressure. So in this theory, this back face, so any inclination of this back face you can consider. Okay, so in this type of geometry of the wall, that you can consider. And again, along this wall back face, so some delta, earlier this delta value is considered to be 0 based on Rankine's theory. However, some angle of wall friction is considered. Okay, so that we will see what is the limit or of this delta, okay, in comparison to the angle of internal friction of the backfill material. So you can point out two major differences in this way in between the Rankine's theory and the Coulomb's theory of earth pressure. Now, after Coulomb's theory of earth pressure, we have learned about different types of retaining wall which are listed below in the slide. So, gravity retaining wall, semi-gravity retaining wall, cantilever retaining wall, counterfort retaining wall, and buttress retaining wall. Okay, so please go through all these retaining walls. What is the use of a specific kind of retaining wall or its suitability for a particular field scenario? So you please go through or learn a little bit about its application. Now, coming to the next segment of this week, that is the design of retaining wall. So this is mostly confined to gravity and cantilever retaining wall. So when we'll go for the design of this specific to retaining walls, gravity and cantilever, so we should satisfy a few conditions. Okay, so suppose the backfill conditions, that is the properties of the backfill, properties of the subsoil, and the geometries of a retaining wall is given to you. Now what you have to check, so as a design engineer or as a practicing engineer, you should ensure that the retaining wall should not fail in sliding, should not fail in overturning, and there is no generation of tension crack at the base of the wall, and they should not fail obviously in bearing fluid. Okay, so these are the 4 conditions which we should check, and it's our responsibility to ensure a safe and satisfactory performance of the wall which is designed with the given geometry, or rather you can also proportion the retaining wall based on this all 4 criteria or 4 conditions. Okay, so as I mentioned earlier that as a geotechnical engineer, either you have to go for proportioning of the wall, like the proportioning of the footing, otherwise, or in other possible scenario, the retaining wall and the geometry of the wall and the properties of the backfill subsoil are given to you. You have to just check whether this retaining wall is safe or not against all these conditions: no sliding, no overturning, no tension, and no bearing. Okay, so we'll see these concepts in more details through some numerical problems in today's session. So we'll first start with this problem. So this problem we couldn't solve in the last week, so due to time limit. So first we'll take this problem and then we'll slowly move into our today's topic. So this is about a vertical retaining wall of 12-meter height supports a subsoil consisting of 2 layers of equal thickness. So I hope you can recall this problem. So similar problem we had solved in the last week. So we had solved this problem for the active condition. Okay, so we'll first read out the problem statement, then we'll see. So the retaining wall is basically supporting 2 layered backfill, and it's having a total height of 12 meter. Okay, so the each layer is having equal thickness, that means 6 meter and 6 meter. The layer 1 is above layer 2 and the remaining properties are given below. The retaining, it should be the retaining wall. So the retaining wall moves in such a way that it mobilizes the passive pressure condition. So you should know what is that condition for which it mobilizes the passive pressure condition. So it should mobilize, it should move in away from the towards the backfill. So if this is the retaining wall, then depending on the movement of the wall, so you will be having 3 kinds of pressure, na? So at rest, when there is no movement, then active and passive. So when the wall is basically moves away from the backfill, so you will be having active pressure. When it moves towards the backfill, means this side, you will be having passive pressure. So it's clearly mentioned in the problem that the retaining wall moves in such a way that it mobilizes the passive pressure condition. In such a case, determine the total passive thrust acting on the wall, and in addition to that, it's mentioned that the water table is at a grade depth. Okay, so there is no effect of water table on the earth pressure distribution. So all the properties or all the parameters are remain same, with the exception that earlier we had solved the problem for active condition. Now in this problem we have to basically determine the lateral earth pressure for the passive condition. Okay, so this is the only difference between these 2 problems, the problems which we have basically considered in the last week and the present problem. So this is the backfill surface, this is the retaining wall, and it's having a total height of 12 meter. So this is layer 1 and this is layer 2. So for layer 1, there is a cohesion of 23 kPa, friction angle 15 degree, and unit weight 15 kilonewton. For layer 2, it's purely cohesionless, so there is no cohesion. Friction angle is 35 degree and the unit weight is 18 kilonewton per meter. Okay. So first we'll determine the passive earth pressure coefficient, because as you know, to determine the distribution of the passive pressure, you should know the passive earth pressure coefficient or coefficient of passive earth pressure for each of these individual layer, that is for layer 1 and layer 2. Now what is the distribution, or what is the analytical form of distribution of passive earth pressure? So if I write in this fashion, that ppz, okay, so z I am measuring from the top of the backfill, so this is the datum for z. So ppz, so this will be gamma z kp plus 2c root under, okay. And I think you know how this equation basically came, okay. So here gamma is the unit weight of the backfill, z this is the depth, kp this is the coefficient of passive earth pressure, and c this is the coefficient of the backfill. So this condition or this expression you have to basically consider separately for each of these layers, okay. So that's why, since we are basically having two layers, so first we'll determine the earth pressure coefficients individually for each of these layers. So kp1, now what is the expression for passive earth pressure coefficient? So this is 1 plus sin phi divided by 1 minus sin phi, okay. So you can rather write it in this fashion, so 1 plus sin phi 1 divided by 1 minus sin phi 1. So 1 indicates, the subscript 1 indicates that this is the property for layer 1, okay. So one minus sin 15 divided by 1 plus sin 15. So this will give you the passive earth pressure coefficient for layer 1 as 0.58. So similarly, kp2, that is the passive earth pressure coefficient for layer 2. So 1 minus sin 35 divided by 1 plus sin 35 divided by 1 minus sin 35. So that means 3.69. Okay. So please check these two values, whether these values are correct or not. Okay. So I think I have missed a mistake. So for calculating the past value, it will be 1 plus sin 15 divided by 1 minus sin 15. So 1.698. Okay, so this value should be 1. Okay. So we have got the two passive earth pressure coefficients. Now we'll start calculating the passive earth pressure distribution. So first we'll calculate it for layer 1. Okay. So first you calculate it for layer 1. So at z equals to 0, what is the pp value? So the pp value should be z equals to 0 means first component will be vanished, so only there will be the second component 2c1 root under kp1. So 2c1 root under kp1. Therefore 2 times the c1 value is 23 and the kp1 value is 1.698. Okay, so this value, हाँ
एक्सक्यूज मी सर, सर फर्स्ट वैल्यू हमने क्यों नहीं कंसीडर किया यहाँ पे?
हाँ which one?
पीपी का जो फर्स्ट है ना,
हाँ
गामा K1, ये जो फर्स्ट वैल्यू है सर, गामा जेड के पी,
हाँ
वो हमने कंसीडर क्यों नहीं किया?
because we are calculating the passive earth pressure at z equals to 0, this level, just at the top
ओके सर,
surface of the vacuum.
यस
Okay,
सर, यस सर, ओके सर।
so you will get this value as 59.94 kPa. Now we'll move on to the next level, that is at the interface, that is at z equals to 6 meter. Now this first component will come into the picture. So we'll be having gamma 1, H1, Kp1. So what is the H1? So suppose we are basically using two different height for different layers. Okay, so this is H1 and this is H2, and both are 6 meters. The thickness of individual layer, so layer 1 and layer 2. Okay, so this value would become gamma 1 H1 Kp1 plus 2 P1 root under Kp1. So this value we have got earlier as 59.94. So this value, the past would be 15 multiplied by 15 multiplied by 6 multiplied by 1.698 plus 2 into 23 into 1. So 59.94 plus 15 multiplied by 6 multiplied by 1.698. So 212.76. 212.76. Okay. So in this way we have got.
सर एक्सक्यूज मी सर,
हाँ
एक्सक्यूज मी सर,
हाँ
जैसे हम Z6 लिए सर,
हाँ
लेयर 1 और 2 के लिए सर, अगर वाटर टेबल अगर 6 मीटर से एबव दिया हुआ, 5 मीटर या 6 मीटर से नीचे दिया हुआ, बिलो अगर 7 मीटर, तो
हाँ.
हाइट H1 हम सर कौन कंसीडर करेंगे सर? वाटर टेबल दिया हुआ है वो, या लेयर पे दिया हुआ है वो सर?
So you are telling me that you are having a water level at a depth of what, 7 meters. Okay, suppose in this location.
टेबल हो तो सर, तो हम कैसे H1 कौन कंसीडर करेंगे सर?
हाँ हाँ हाँ
7 मीटर या लेयर 1 का जो ये मिडिल पार्ट है 6 मीटर, तो वो कंसीडर करेंगे?
Okay, so we are having water table at a depth of 7 meters.
यस सर।
Okay, so now please see from this picture. So first of all, 6 meter, this level is basically the.
H1 6 मीटर या 7 मीटर?
हाँ हाँ
सर मतलब ये जो H1 वैल्यू है सर, तो लेयर के हिसाब से कंसीडर करेंगे या वाटर टेबल के हिसाब से?
No, this H1 and H2 basically we have introduced only for the sake of calculation. So there is nothing to do with this H1 and H2. Okay. Suppose I'm discussing about this. Suppose you are having the interface at a depth of 6 meter and you are having the water table location at a depth of 7 meter. So first of all, you have to calculate the earth pressure for layer 1 completely. So that means the top of layer 1 and the bottom of layer 1. So now the top of layer 1 is z equals to 0 meter and bottom of layer 1 is z equals to 6 meter. Okay. So this will calculate in the usual fashion, what just now we have did. Okay. So this is the standard procedure. So we have already done it and this will remain same. There will not be any change in the calculation part. Now what we'll do, For this water table location, we'll have to calculate the passive earth pressure at this level separately, means at a depth of 7 meters. So as per the previous problem,
सर वाट
हाँ
वाटर टेबल के हिसाब से सर सिंगल कैलकुलेशन अलग से करना पड़ेगा सर.
हाँ. So at z equals to 7 meter, we have to calculate the pp value, and for the calculation of this pp value, this should be gamma 1 h1 plus gamma 2 submerge. Okay, sorry, not gamma 2 submerge, gamma 2 multiplied by this thickness. Okay, suppose you, for the sake of calculation, you want to introduce a separate thickness or separate variable h2, and then this become h3. Okay, so this is basically as per your convenience. So this is not any standard rule. So what is the fundamental to calculate passive earth pressure? First, you have to calculate the vertical overburden at that level. Yes or no? So
यस सर.
we are trying.
दो कैलकुलेशन करना पड़ेगा ना सर, एक
हाँ
6 to 7 मीटर के बीच में सर, और एक 7 to 12 मीटर के बीच में सर, दो कैलकुलेशन करना पड़ेगा सर.
No. Right
ये वाटर
now,
टेबल का डेप्थ के हिसाब से सर.
no. Let me finish. Right now we are basically dealing with 7 meter level. Okay, so we are not dealing with 12 meter level. So we are basically moving from the top towards the bottom. So we have calculated the passive earth pressure at top, that is z equals to 0 meter. We have calculated the passive earth pressure at the interface in between two layers, that is at z equals to 6 meter. Now, okay, before that you have to also calculate the passive earth pressure at the same z equals to 6 meter, but for layer 2, which we didn't calculate. Okay, so in between you have stopped me, so we'll have to calculate that part also. Now once you enter into the layer 2, you are having a water table location at a depth of 7 meter. So that's why you have to calculate the passive earth pressure at this level also, at 7 meter. Otherwise, you can directly move on to the level that is at the base of the retaining wall, z equals to 12 meter. Now since you are having a water table location in between layer 2 and at a depth of 7 meter, so you have to calculate the passive earth pressure. Now how you can calculate the passive earth pressure at 7 meter? That is the question. So for that, first you have to calculate the vertical overburden up to this 7 meter depth. Up to this 7 meter depth. So that will give you this gamma z component. Gamma z is nothing but the vertical overburden. Are you getting my point? This gamma z
Yes, sir.
contribution is giving you the vertical overburden. The physical significance of this gamma z value, this is the vertical overburden. Now how you can calculate the vertical overburden? So for calculating the gamma z value up to this 7 meter, you will be having two different unit weights. So one for layer 1 and another one for layer 2. So that's why this gamma z you have to calculate separately. So first gamma 1 h1 in the sense this thickness, the total thickness of layer 1, and then gamma 2, then this small thickness up to 7 meter level. So plus gamma 2, suppose we are introducing it as h3, this part as h3. Now what is the value of this h3? The value of this h3 is 7 minus 6, that is 1. Is it clear? Then you have to multiply then you have to multiply it with the coefficient of passive earth pressure of the respective layer, that is for layer 2. Since this level is coming under layer 2, so you have to multiply this value with the layer 2 coefficient of passive earth pressure. Okay, then the second component 2C2 Kp2, because layer 2 doesn't have any cohesion, so second component will not be there. So only this part will basically calculate the passive earth pressure at layer 2 in at a depth of 7 meters in layer. Is it clear?
Yes, sir. Clear.
Okay. So this is for when there is a water table in layer 2. However, for the present problem, there is no water table, so we will not consider this level separately. Okay. So for the sake of
Okay, sir.
calculation, we have divided, or we have considered two additional variables called h1 and h2. Okay. Okay. So this will be for the water table case. Okay. Now we have calculated the passive earth pressure at the top of layer 1 and bottom of layer 1. Now similarly, we'll calculate the passive earth pressure for top of layer 2 and bottom of layer 2. Now what is the top of layer 2? Top of layer 2 is z equals to 6 meter. Okay. As you can see from this picture, top of layer 2 is basically z equals to 6 meter. So what will be the PP value? So PP would be gamma 1 H1. So this is the vertical overburden. Okay, at z equals to 6 meter. Gamma 1 H1. This will not change. Now what will change? The passive earth pressure coefficient will change, because now you are in layer 2. So this will be Kp2. And again, since layer 2 doesn't have any equation, so the second component will not be there. This would be the only one term for calculating the passive earth pressure at the top of the layer 2. So 15 multiplied by 6 multiplied by 3.690. So C 32.10. Now we'll calculate the last one, that is the base of the wall or bottom of layer 2, that is z equals to 2 meter. So PP value would be gamma 1 H1 plus gamma 2 H2. Because up to the base of the wall, you will be having two layers, layer 1 and layer 2, and these two layers are having different unit weight, so therefore you have to calculate the vertical overburden separately. So for first one, this will be gamma 1 H1 thickness of layer 1, and then gamma 2 H2 thickness of layer 2, multiplied by the coefficient of earth pressure of layer 2, passive earth pressure of layer 2. So gamma 1 H1 15 multiplied by 6 plus gamma 2, that is I hope 18 multiplied by 6 into 3.9. So you will get 730.62 as the passive earth pressure at the base of the wall. Okay. Now we'll draw the distribution. So how does it look like? Okay. So this is the wall. This is 0 meter. This is 6 meter, and this is 12 meter. Okay, so first we'll start from some value 59.94. Then we'll come to the interface. Okay, so interface from the first layer. So at the interface we will be having two different values. So 1200, 1200, 212.76 and 332.10. So one from first layer and another one from second layer. So the upper value, this will be 212.76. Then we'll start from slightly greater value, not slightly, Okay, so for the lower part it will be having 332.10 and then at the base 730.62. So this is the passive earth pressure distribution. Obviously in KP. Now what we have to do? We have to basically determine the resultant passive thrust. So we have to calculate the
Excuse me, sir.
tell me.
सर ये जो डायग्राम है सर, डिस्ट्रीब्यूशन डायग्राम,
हाँ
के टू उस कंडीशन में
sorry, I didn't get you. You in between your voice was cracking. So can you please repeat the question again?
सर केपी वन का वैल्यू अगर excuse me, सर ये जो डिस्ट्रीब्यूशन डायग्राम है सर,
हाँ
उसमें केपी वन का वैल्यू अगर ज्यादा हो और केपी टू का वैल्यू कम, तो फिर डायग्राम सर, ये डिस्ट्रीब्यूशन डायग्राम कैसे है सर?
So obviously this distribution will not be this one. So you are for this problem your kp1 is less than kp2. Okay, now you are telling me that kp1 is greater than kp2. So
यस सर.
at the interface you have to check basically. Okay, so since we don't know about these two values, so I think at this moment it will be difficult to conclude, because for the first layer you are having, okay, so can you please give some example for kp1 and kp2 values? Okay, we are taking the reverse way. Okay, so kp1 we are taking it as 3.690 and kp2 as 1.698. Okay, so we are
Okay
taking
sir,
it
okay
as
sir,
in
yes
the
sir.
reverse way. So gamma 1 this is 15, then the h value this is the 6 multiplied by 3.690 plus cohesion component is there, so 2 multiplied by what is the cohesion part? 23. So 23 into 3.690, 90 into 3.690 plus 2 into 23 into 3.690. So it's giving you a value of 470.46. Okay, so this is for layer 1. Now for layer 2 it will be 15.6 into 1.698, obviously lesser than from the previous value. So 15 into 6 into 1.698, only 152.82. So therefore the distribution should look like this way. Sorry, so first it will be having some greater value, then the distribution starts from something like. Is it clear? So for first
Thank you sir,
layer
yes sir, clear sir.
420.46, and for the second layer it will be 152.82. So this value we have to check whether this is exceeding this 420.96 means at the bottom or not. That depends on the calculation. Okay. Okay. Now
Okay sir.
now we'll calculate the passive thrust. That is the resultant of the passive earth pressure distribution. So to calculate this resultant, you have to basically calculate the area of the these two values, these two blocks, so 1 and 2, and these two blocks are trapezoidal in nature. Okay, so the distribution is basically trapezoidal for each of these individual layers. So the total passive thrust, this will be summation of A1 plus A2. Now how to calculate the area of a trapezium? So this is, what is the formula for calculate to calculate the area of a trapezium? Height by 2 multiplied by summation of two sides, na, b1 plus b2. So suppose this is one side b1, this is the second one b2, and this is the height. This is the height. Okay. Otherwise, you can split this diagram into a rectangle and triangle. Then also you can calculate. Okay. But what will happen? So in that case, your calculation will be a little bit lengthy. Okay. Nothing else. So we'll basically calculate it from the area of a trapezium. So 6 divided by 2, then 59.94 plus 212.7. This is for the upper trapezium, and for the lower trapezium, this will be again 6 by 2, 332.10 plus 730. So I am getting something 4006.26 kilonewton. So this is the answer. Now the next question is, at what level this resultant passive thrust will act from the base of the wall. Suppose this is the base or reference line or datum line. Now from this base of the wall, at what level this PP should act? Okay, so suppose I am considering the PP is acting at a distance of z bar from the wall base. Now how to calculate this z bar? So can you please let me know how to calculate this z bar? So this z bar can be calculated by taking the moment of individual forces above the base. So A1 Z1 bar plus A2 Z2 bar divided by A1 plus A2. Now A1, A2 we know. Now what is Z1 and Z2 bar? Z1 and Z2 bar, these are basically the line of action of individual forces. So suppose this is the line of action for the first component, and secondly this is the line of action for the second component. And it's very easy to calculate Z1 bar and Z2 bar. This is based on the basic geometry. Okay, so you have to calculate the center of gravity of the first trapezium, then you have to add it with the height of the second trapezium, you will get Z1 bar, and if you know the CG of the second trapezium, so simply that will give you the Z2 bar. So you know Z1 bar, Z2 bar, you know A1 and A2, so you can easily calculate the line of action of the resultant passive thrust from the base of the wall. Okay, so we will not do that calculation here. So this is a homework for you. So please do it at your home. Okay, and let me know about the value of z bar. Now we'll take the second problem. So second problem, this is the 10-meter high retaining wall supports a cohesionless backfill which has a surface inclined at an angle of 20 degree with the horizontal. If the unit weight of the backfill is 18 kilonewton per meter cube and the angle of internal friction is 30 degree, determine the horizontal component of total active thrust acting on the wall per meter. So this talks about the retaining wall like this. So this is the retaining wall. This retaining wall is having a height of 10 meter and the backfill surface is now inclined. It's not horizontal or level as in the previous problem, and the inclination angle is 20 degree. And the backfill is having the properties like internal angle of internal friction is 30 degree and gamma is your 18 kilonewton per meter square. So gamma is equal to 18 kilonewton per meter cube and pi value is. Now what you have to determine? You have to find out the horizontal component of the total active thrust. Now as you know, the total active thrust will not be horizontal. Okay, so unlike the previous problem. So in the previous problem, the active thrust acts like in this fashion. Suppose this is the retaining wall surface. So this is the lateral earth pressure or active thrust is acting on the wall. Why? Because the backfill surface didn't have any inclination. It was leveled. So therefore, this active thrust doesn't have any vertical component. However, in the present problem, since the backfill surface is having an inclination of 20 degree, so this resultant active thrust will be having two components, and the resultant active thrust, this will be basically inclined with the same angle as of the backfill surface. Okay, so this angle will be same 20 degree. Now this resultant active thrust will have two components. So this is the horizontal component and this is the vertical component. Okay, 20 degree. So this is the resultant active thrust. So this is the vertical component and this is the horizontal component. Now you have to calculate the basically this horizontal component. Now how you can determine this horizontal component? This horizontal component, determination of this horizontal component is very easy. So this will be PA cos I. You have to resolve this PA into components. So this will be PAH will be PA cos I and PAB will be PA. Okay, this second part is not needed for the problem. Now I we know 20 degrees, so PA you have to only calculate. Now this PA, this will be half KA gamma H square. Now what is K? This is the coefficient of active earth pressure. Gamma, this is the unit weight of backfill material, which is 18 kilonewton per meter cube. And what is H? This is the height of the return 10 meter. So therefore you know gamma KH, HK gamma. So you can determine the PA, and if you know PA, you can determine the horizontal component of this PA. Now, what is the value of Ka? So, is it 1 minus sin phi by 1 plus sin phi? So, we know na, that as per or based on Rankine's theory, the active earth pressure coefficient is 1 minus sin phi by 1 plus sin phi. So, will this coefficient of active earth pressure will be valid for this problem as well? No, this will not be valid, because now the backfill surface is inclined in contrast to the level backfill surface as considered to basically derive this equation. So now this active earth pressure coefficient would be, so there will be a slight modification. So cos I multiplied by cos square I minus cos square phi, sorry, divided by cos I cos square I minus cos square phi multiplied by. Okay. Now you compare this equation with the previous one and substitute the value of I as 0. I equals to 0 means you are basically considering a horizontal backfill surface, a level backfill surface. Okay. So no inclination. Now if I becomes 0, then what would be the value for K? This will be 1 minus cos square phi divided by 1 plus root under 1 minus cos square phi multiplied by cos 0, that means this is also 1. So that means 1 minus, now what is root under 1 minus cos square phi? So 1 minus cos square phi is nothing but sin square phi, and root under sin square phi is sin phi. So 1 minus sin phi divided by similarly 1 plus sin phi. So it goes back to the earlier scenario where the horizontal, the backfill surface, the top of the backfill surface was assumed to be horizontal. Okay, so that means this is the most generalized scenario. You can basically consider the provision for inclined backfill surface. So inclination of backfill surface is basically considered in this expression. And if you put I equals to 0, that means for a horizontal backfill surface, so you can easily get the expression as 1 minus sin phi divided by 1 plus sin phi. Okay, but this is not the case for this problem. So we'll first calculate this Ka. So the I value is 20 degree, phi value is 30 degree, and using these two values we will first calculate the Ka value. So please calculate and let me know. Please calculate. So I am getting some value as 0.414. Okay. So this value as 0.4. Therefore, your horizontal component of the resultant active thrust will be half Ka gamma h square into cos I. Half Ka gamma h square, or rather we can say first write in this question. Into half 0.4, gamma value is 0.80 square. So 350, approximately 350 millimeter. Is it okay? So if you want to calculate the vertical component as well, just you have to take the sine component. So PA sin I will give you the PAV. Okay. However, that is not required for this problem. Now we'll take the third problem. So this problem is mentioned like that: the soil conditions adjacent to a rigid retaining wall are shown in figure below. A surcharge pressure of 50 kPa is carried on the surface behind the wall. Now for soil A above the water table, the C prime value is 0, phi prime 38 degree, gamma prime 18 kilonewton per meter cube. For soil B, that is below the water table, C prime is 10 kPa, phi prime 28 degree, and gamma sat 20 kilonewton per meter cube. Calculate the maximum unit active thrust in kPa behind the wall. So here we need not to calculate the resultant active thrust, rather we have to find out the maximum unit active thrust. However, for that also we have to first establish the active earth pressure distribution behind the wall. Okay. So I think some of you were asking me in the first problem about the introduction of a water table in that problem. So here that part you can see very easily. Okay. So this is also a two-layered backfill. So layer A and layer B, and at the interface we are having the groundwater table. Okay. So where the layer each layer doesn't have equal thickness, rather the layer A is having a thickness of 6 meter, which is greater than the thickness of layer B, which is 3 meter. Okay. So however, in this problem there is a surcharge. So this surcharge we didn't basically consider in the previous problem. Now due to this surcharge, application of this surcharge, the active earth pressure distribution, so PA Z, so this will be modified. So this will be gamma Z KA minus 2C root under KA plus. So this is the additional term which will get due to the application of this surcharge. Okay. Now since the problem is having two layered backfill, so we'll first calculate the active earth pressure coefficient for both this layer. So for first layer it will be 1 minus sin 30 divided by 1 plus sin 30. So please cooperate with me for the calculation part, and for the second layer it will be 1 minus sin 28 divided by 1 plus sin 28. So please let me know what are the values of Ka1 and Ka2?
0.54, sir.
0.54 for
Ka1 is, sir, 0.542.
And for layer 2 or layer B, this is
0.573, sir. Ka2.
0.573.
Yes, sir.
How? But I am getting some different value. You are considering 1 minus sin 28 by 1 plus sin 28, na?
Yes, sir.
Even for the first case also I am getting a different value. How you are getting as 0.542? This is 1 minus sin 38 divided by 1 plus sin 38. I am getting 0.238 only. Can you please cross check this value?
In my calculator, so sir, 0.542. I don't know.
No. 0.542. How you can get 0. What is the value of sine 38? First, let me know.
Sir,
Then,
sin 31, 1 minus sin 38 divided by 1 plus sin 38.
no. I am asking about what is the value of sine 38. Then I can answer you. Maybe what is the mistake you are doing. What is the value of sine 38?
0.296.
No, I think then you are basically taking the input in radian. Because sine 38, how you can get it as 0. What value you are getting? 0.298, na? So
Yes, sir.
this is the wrong value, because sine 30 we know this value is 0.5, and as you increase the value of means this theta, so sine value will basically go on increasing. So 0 it's 0, 30 degree it's half, and then 90 degree it's 1. So in between we are getting 38, in between 30 and 90. So it should be in between 0.5 and 1, but you are getting the value lesser than 0.5. So it should not be possible. So what I am getting, it's a 0.616, and it seems to be reasonable. So 1 minus 0.616 divided by 1 plus 0.616. So that's giving me the earth pressure coefficient, active earth pressure coefficient as 0.23. So I hope there is a mistake in the settings of your calculator. So please cross check, okay?
Yes, sir. I think so.
Because in radian maybe that is possible. Okay. So please cross check. So anyone else can ensure whether you are getting the same issue or not? Okay, so we'll proceed with these two values only. So we'll at the end cross-check this answer, what we have basically uh, done earlier. Okay, so that we'll check. Okay, now we'll start calculating the passive earth pressure distribution. So layer 1 first, layer A. So Z equals to 0 meter. So this PA value, this will be obviously first component is 0. So there will be a second component will also be 0, because C prime, the first layer is basically purely questionless. So there will be only this third component, that is QKA. So Q times KA1. So Q is your 50 multiplied by 0.338. Okay. So 11.9. Now coming to the bottom of layer B, that is Z equals to 6 meter. So PA would be gamma 1 H1 K1 plus QK1. Gamma 1 value is your 18, H1 6, K1 0.238 plus 15 0.50. Okay, 37.6 I am getting. Now we'll consider layer B. So layer B, Z equals to 6 meter. Here will be gamma 1 H1 Ka2 minus 2C root under Ka2. Okay, so layer 2 is your cohesive frictional, so there will be minus 2C. So this is the reverse scenario for problem as compared to problem 1. So problem 1, the upper one was cohesive frictional, lower one was purely cohesionless. Here the upper one is purely cohesionless, whether the lower one is cohesive frictional. Okay, last. Okay. 18 multiplied by 6 multiplied by Ka2 value is your 0.361 minus 2 multiplied by the C value is your C2 10 multiplied by root under 0.361 plus 0.361. So I am getting 45.02. So please cross check these values. Then Z equals to 9 meter. Now Z equals to 9 meter. This is crucial because this value will give you the maximum unit active thrust. Okay. So as per my understanding, now we'll check what happens. So first of all, the saturated unit weight of layer B is given as 20 kilonewton per meter cube. However, as you can see that the water table is basically at the interface in between two layers, soil A and soil B. So therefore, for soil B, when you will be calculating the effective overburden, so you have to consider the submerged unit weight of soil B. So therefore, the submerged unit weight you have to calculate beforehand. So this will be 10 minus 20, that is 10 kilonewton per meter cube. Okay, because 10, this is the saturated minus the gamma W. Gamma sat minus gamma W will give you the submerged unit weight for layer B. So first we'll write the analytical form. So this will be gamma 1 H1 plus gamma 2 prime H2. Why gamma 2 prime? Because now the soil is entirely submerged. Okay, so this is the gamma 2 prime. Okay, rather we can use gamma prime. Okay, then K2 minus 2C2 K2 plus QK2 plus gamma W H2. This is for the pore water pressure. Okay, so this lateral pressure is contributed by the pore water pressure. Since we are having the water table in this problem, so we have to add this pore water pressure. So 18 multiplied by 6 plus 10 multiplied by 3 into 0.361 minus 2 into 10 into 0.361 plus 50 into 0.361 plus 10 multiplied by. So quickly tell me what would be the value of active earth pressure at the bottom of the wall. So I am getting 85.85. Okay, so now we'll try to draw the distribution. So this is 0, this is 6, 9. So first we started from 11.9. We started from some value 11.9. Then we reached the interface in layer 1 as 37.60. 37.60. Then at the same interface, however, for layer B, we are having a slightly greater value, 45.02. Okay, so 45.02 and finally 85.85. Okay, so this distribution you can represent in a different fashion. How? So, and this is the better way to represent. So this is 30 and this is 55.55. Sorry, 55.8. So this is the active earth pressure distribution. Now, why I have basically separated or I have basically put two distribution for representing the active earth pressure, because the first three terms will give you the active earth pressure without considering the pore water pressure contribution. Okay, and the second component will give you the pore water pressure contribution, and it will only be valid in the second layer, since you are having the groundwater table location at the interface. So therefore it's better to represent the active earth pressure distribution in this fashion. So 55.85 plus 30, so as a whole 85.85 will give you the maximum unit active thrust on the wall, and that is asked in this problem. So calculate the maximum unit active thrust behind the wall. So that will be 85.85. So maximum unit active thrust behind the wall is 85.85. Okay. Is it clear?
Yes, sir.
Okay. So now we'll take our next problem. So the next problem, a 12-meter high retaining wall supports a two-layer subsoil. Properties given below. The water table is at a depth of 5 meters from the ground surface. Now we have to find out two values. So first of all, the total lateral force that would act on the retaining wall under active earth pressure conditions after the formation of tension crack. So this is component A, and for component B we have to figure out or find out the distance between the point of application of lateral thrust on the wall and the base of the retaining wall. So this is the problem statement. So for layer 1, we are having the water table location. So in the layer 1 itself, we are having the water table. So layer 1 is having a height of thickness of 8 meter, whereas the layer 2 is having a thickness of 4 meter. So the total retaining wall height is 12 meter, and it's supporting two layered backfill. So the first layer or the top layer is having a thickness of 8 meter, and the bottom layer or second layer is having a thickness of 4 meter. And the water table is found at a depth of 5 meter from the top of the backfill. And the properties of the two layers are basically mentioned. Okay, layer 2 is basically having thickness more than 4 meters. So it's having a thickness of 14 minus 8, 6 meters. However, for our calculation, we'll restrict the thickness of layer 2 up to 4 meters. Okay, so because the retaining wall height is 12 meters, so 8 plus 4, that will give you the entire height of the. Okay, so we'll not go into much details, because similar kind of problem, we are solving similar kind of problem again and again. So we'll quickly solve this problem. So first we'll calculate the active earth pressure coefficients for both the layers. So K1, and let me know the values which you are getting. Okay, so 1 minus sin 25 divided by 1 plus sin 25, then Ka2 1 minus sin 30 divided by 1 plus sin 30.
First value is 0.405.
Okay, so 0.406. Okay, this time you are getting the correct one. Okay, and then I think this should be 0.
0.33, sir.
Okay, now again the distribution of PAJ. So this will follow this pattern, gamma z Ka minus 2C Ka. Again, all the expression which I am putting, this is for the cohesive frictional part. Okay, so accordingly you have to judge. So whether the soil is purely cohesionless, purely cohesive, or cohesive frictional, both. Okay. Now we'll basically start calculating the distribution. So for layer 1, so here I am calculating. So z equals to 0. So PA value would be what? PA value would be what?
Z0, sir, the first value is 0. 2C into root under Ka.
Okay, so minus 2C1 root under Ka1. Now what is the value of C1 or cohesion for layer 1? The value of cohesion for
30 by
layer
2, sir.
This is U by 2, or here we can write U basically U by 2, that means 15 kilonewton per meter square. And for the second layer, the value is 20 by 2, that is 10 kilonewton per meter. So please notice that here both the layers are basically cohesive frictional. Okay, so that means minus 2 into 15 into 0.40. So what is the value you are getting? Minus 19.12 ppm. That means we are getting tension at the top of the pipe. So obviously you have to calculate the depth of tension crack. So how to calculate the depth of tension crack? So the depth of tension crack we can calculate by equating this PA to 0. And if you equate the PA to 0, then the depth of tension crack you can calculate from this expression. P1 by gamma 1 2 multiplied by 15, the gamma value is your 16 multiplied by root under 0.406. Okay. So 2.94 meter. I am getting this value. And at this level, your PA value should become 0. Applying that condition, we have figured out the value of Z0. Okay. Now we'll move on to the water table location. That means Z equals to 5 meter. Now what will be the PA value at Z equals to 5 meter? What will be the PA value? So the PA value would be the first the gamma 1 Z1. So gamma 1 is your 16, then Z1 is your 5 multiplied by 0.406 minus this one 19.14. Okay, minus 2c root k1. So 16 into 5 into 0.406 minus 19.12. So I am getting 13.36. Now we'll come to the interface, that is Z equals to 8 meter. So first we will calculate the pressure for layer 1, then we will calculate it for layer 2. So PA would be 16 multiplied by 5 plus 6 multiplied by. So we have to consider two separate components. So first component will be for above the water table and second component will be for below the water table. So above the water table you have to use the gamma sat, that is the bulk one, but below the water table you have to consider the submerged unit weight. And what will be the submerged unit weight? That is the saturated unit weight minus the unit weight of water. That means 16 minus 10, that is 6 multiplied by the remaining height. Here the remaining height to reach the interface is 8 minus 5, that is 3 meter. Okay, that multiplied by the pressure coefficient 0.406 minus 19.1. So what value you are getting? 16 multiplied 5, that is 80 plus 18 multiplied by 0.406 minus 19.1. So I am getting 20.67. But this will not complete the answer. Complete the lateral earth pressure at this level. This plus you will be having the contribution from the water pressure. So 10 multiplied by 20.67 or 67 plus 3. So that means 50.67. This is for layer 1. Okay. Now we'll proceed for layer 2. So layer 2 will start from Z equals to 8 meter. So at the same interface, you will be having a different PA value. So PA would be 16 multiplied by 5 plus 6 multiplied by 3 multiplied by the coefficient of active earth pressure from layer 2, and this value is now 0.333 minus 2C2 Ka2. Okay, so this question you have to take it from the second layer, not from the first layer. So what is the value of C? The value of C is now 10 root under 0.333 plus 10 multiplied by, so this is for the water pressure. Okay.
सर ये 10 सर कैसे, ये जो 10 सर आपने जो लिया ना सी की जगह पे सर,
हाँ, this is you are calculating for layer 2 ना.
ओ तो सर 20 माइनस 10 जो सबमर्ज ओके
हाँ.
सैचुरेटेड सॉइल से माइनस किया ओके सर.
No. This is not the urine oil. This is the coefficient of layer 2. 2 times C2. This is 2 C2 root under Ka2. Now what is the value of C2? That means coefficient of layer 2. This is 20 by 2 na. Already we have calculated 20 by 2, 10. We are at the same interface. However, we are calculating it for layer 2, not for layer 1. When you will calculate it for layer 1, you have to consider C1, that is 15 kPa. However, for layer 2, it will be 10 kPa. Is it okay?
सर तो गामा सैचुरेटेड से डिवाइड करना है सर.
No. How you are getting the gamma saturated? Okay, first let me put the analytical part. So at the interface, what will be the effective overburden? What will be the effective overburden? 16 gamma, okay, 16 multiplied by 5 plus 16 minus 10 multiplied by 3. Yes or no? This is above the water table and this is below the water table. Yes or no?
Yes sir.
This is
Yes, sir.
this is the gamma z component total multiplied by Ka2, because you are now dealing with the layer 2. You are at the interface, but you are calculating the PA value for layer 2. So this is the value of Ka2. Okay. Minus 2C2K2. Now what is the value of C2? What is the value of C2? This is 10 na? This is 10 only na? Because unconfined compressive strength of layer 2 is 20 kPa. So this is QU by 2. That means 10 kPa.
अगर सर जो सेकेंड लेयर में अगर वो जो कन्फाइंड स्वेल का मतलब वैल्यू ना दिया हो, तो अगर 0 दिया हो तो सर वहां पे नहीं ले सकते हम सर.
No, then this entire term will be 0. If this is positionless, then second component will be not there. That's why I am discussing.
ये जो बाकी वाला पार्ट है वो नहीं रहेगा सर.
नहीं, this 2 times 10 root under 0.333 will not be there, but this port pressure component will be there because you are having the groundwater table. Is it clear? So first component will be there and third
Yes, sir.
component will be there. Second component will not be there since you are not having any cohesion. Second component will only be there if you have cohesion, and that the appropriate cohesion value you should take.
नहीं दिया हो तो.
Okay.
Okay sir.
Okay, so please calculate and let me know the value of PA in layer 2, but at z equals to 8 meter. So I hope it will be 21.09 plus 30. That means 51.09. Okay, then finally we'll calculate the PA value for Z equals to 12 meter. So this will be 16. Now please check how many components will be there in the gamma Z part. Okay, so 16 multiplied by 5, then 6 multiplied by 3. This is for layer 1. For layer 2, again you have to calculate the saturated unit weight, submerged unit weight, then you have to multiply the respective thickness. Now submerged unit weight, what will be the value of submerged unit weight? It will be 10 multiplied by 4. Have you got this? This is for layer 1. 16 multiplied by 5. This is above the water table. Okay. 16 multiplied by 5. This is above the water table. Then 6 multiplied by 3. This is below the water table, however, up to the interface. Then 10 multiplied by 4. That is the thickness of layer 2 up to the base of the wall and the submerged unit weight of layer 2. Now, what is the submerged unit weight of layer 2? That is 10 kilonewton per meter cube. Okay. So, here I am writing gamma prime is your 10 kilonewton per meter cube, and here gamma prime is your 6 kilonewton per meter cube. Okay, is it fine? So this is the additional term coming from layer 2. Then this 2C2Ka2, it will remain same. However, for the pore water pressure, now this depth would become 7. How? Because this is the 12 meter level, this is the 5 meter. So the distribution you will be have for a depth of 7 meter. 12 minus 5, that will give you 7 meter. Now if you calculate, then this value would be 34.41 plus 70. 34.41 up to this part. Okay, second part. So that means 104 kp. Should I move further?
Okay, sir.
Okay. So now I will draw the distribution. So this is your 0. Then this is your 5 meter. Where we have encountered the water table. Then this is your 8 meter, the interface, and then this is your 12 meter. Okay. So this is the retaining wall height. Now we'll start from some negative value as we have got. So this is negative. So we have got the negative value as 19.12. This is 19.12. Then at 5 meter we have got 13.36. Okay, so this value is your 13.36. Then we have got the value of PA at the interface as 50.67. Now out of this 50.67, 30 is from the pore water pressure. So okay, it should follow the same gradient. Okay, so this value is your 20.6 plus you will be having the pore water contribution, the contribution from the pore water pressure, and this value is your 30. Okay, and lastly, okay, not lastly, because at the same interface we'll be having the pressure at 21.09 from layer 2 to a slightly higher value. Okay, 21.09. From first layer this is 20.67, and from the second layer it is 21.09. And at the base we will be having 34.41. This is the active pressure distribution. This is in KPA. And what is this side? So this side is your Z0. So please let me know if you have any confusions or any doubts. So we have started from minus 19.12 kPa at the top, then at Z0 equals to 10.94 meter, 0 active earth pressure, then at the water table location 13.36 kPa, then at the interface 20.67. This is for the soil part, and means the effective overburden part, and this is for the pore water part. Okay, so that if you are asked to determine the total active earth pressure at the level of 8 meter, then you have to basically add these two components, 20.67 plus 30, as I mentioned earlier, 20.67 plus 30, then only you can get the complete answer, 50.67 kPa. However, for representation I have put it in separate fashion, okay, to in basically two different component fashion. Okay, now at the same interface for layer 2 we are having 21.09, a slightly higher value. So we'll start from 21.09. We have started from 21.09 and we have reached the bottom of the wall with a value of 34.41. So 34.41 plus 70, that is 104.41, will give you the total active earth pressure at the base of the wall. And at the interface from layer 2, the total active earth pressure is 21.09 plus 30, that means 51.09. Is it okay?
सर जो लास्ट वाला है ना 34.41 और 70 को जो टोटल करके
हाँ हाँ टेल मी.
तो सर ये जो 10 सर ये जो
Your voice is cracking.
sir.
I didn't get you. Can you please repeat the question? Means you are asking about this third component 10 into 7. How I get this part?
यस सर, जो वाटर टेबल से जो अति बेस तक का डिस्टेंस है 7 मीटर सर, उसको सर मल्टीप्लाई किए हो सर अति से जो गामा डब्ल्यू है या सबमर्ज।
Exactly. So this is the water table location. So 12 minus 5, 7 multiplied by gamma W. This is the unit weight of water, gamma W. So that will give you the pore water pressure at the base of the valve. Okay.
Okay sir. Thank you sir. Yes sir.
Okay. Now we'll come back to the problem statement. So in the problem statement, it was asked that we have to find out the total lateral force that would act on the retaining wall under active earth pressure conditions after the formation of tension crack. So therefore, you have to be very careful. We basically solved similar kind of problem in the last session. So once the tension crack is basically formed, there will not be any basically any what I can say, any connection between the soil and the retaining wall. So the soil in the tension part will be separated from the wall. So that means this part, the above part, you have to ignore. So after formation of tension crack, the distribution will be modified. So how this distribution will be modified? So it will basically start from the positive value on. So this is 2.94 meter. This is 0, and this is your 8 meter. In between we will be having 5 meter and then 12 meter. Okay, so class. Okay, so this is your 30, this is 70, 34.41, this is 21.09, and this is 20.67, and this is 30. So this will be the distribution, and accordingly you have to calculate the total active force. Now if we try to determine the total active force, you have to consider the basic what I can say, the basic diagram, that is the I can split this diagram as one, okay, or the total one as one, then two, and this one is three. Okay, now we'll try to calculate one by one. 1, 2, 3. Now I think it will be better to put in this section 1, 2, 3. Okay, now what is PAI, and this is the data. Now what is the area of this block? That will give you the active force, total active force for this diagram. Okay, now what is the area? So the area is basically half into 5 minus 2.94 into 13.36. Okay, so the area is basically half into 5 minus 2.94 multiplied by 13.36. So please calculate and let me know. Okay. Okay. Now we'll calculate this Z bar. This is from base of the wall, because we have to find out the application of this total active force also. So that's why we will calculate it simultaneously. So the application of this PA1 from the base, it will be 5 plus this is the height of this triangle, that by 3. Okay, so 7 plus 5 minus 2.94 by
सर पीएआई का वैल्यू है सर 13.76.
13.76. Okay, so this is
Yes sir.
kilonewton per meter.
And second value is 0.68.
Sorry, 7.69.
68. Yes sir. Yes sir.
You have to add this 7, na? So the CG
Yes
we
sir.
have
Yes sir. Yes
calculated,
sir.
then you have to add the 7. Okay. Now coming to second component, so this is basically trapezium, as you can see. So that value you can calculate in this fashion: 8 minus 5 by 2. This is the height of the trapezium, multiplied by 13.36 plus 20.67. And for CG, this will be 4 meter, because this is the 4 meter. Then you have to calculate from this the CG. So the CG would be 20.67 plus 2 times 13.36 divided by 20.67, 13.36 plus 4.
First value is sir 51.40. सेकेंड का सर ये जो जेड आई है सर उसका सर 5.4 सर।
This one.
यस सर।
Okay. Then calculate the remaining value. Have you got all the values? I have listed here, okay?
ओके सर।
So you can calculate at your home and please let me know whether these values are correct or not. Okay. Now we'll, okay. So just let me add one slide here.
सर ये जो हमारे प्रॉब्लम ये जो था ना सर 4 नंबर इसका सर फर्स्ट पेज सर एक बार आइए ना सर, थोड़ा डाउट है।
1 minute. Huh?
ओके सर।
Tell me, what is the problem?
सर प्रॉब्लम 4 का सर फर्स्ट पेज पे सर आइए तो सर।
In this slide?
No sir, first slide. In this problem, sir, first slide, sir.
This one?
Yes, sir. Sir, yes, sir. जो हमारा वाटर टेबल दिया है 5 मीटर पे सर, और सेकेंड लेयर है सर 8 मीटर। अगर हमें दिया गया हो अगर वाटर टेबल 9 मीटर पे सर, तो जो सेकेंड लेयर हम कंसीडर करेंगे सर वो 9 मीटर से कंसीडर करेंगे 14 मीटर तक, या सर 8 मीटर से 14 मीटर तक कंसीडर करेंगे सर?
No, you have to consider it from the 8 meter only. So at the 8 meter
Because
you have to
मतलब
calculate the lateral earth pressure, then again you have to calculate the lateral earth pressure at 9 meter.
ये जो सर जेड 8 मीटर पे सर आपने जो कंसीडर किया हुआ है सर कैलकुलेशन, वहाँ पे अगर 9 मीटर टेबल वाटर डेप्थ दिया हुआ हो तो हम सर जेड 9 मीटर पे कैलकुलेट नहीं करेंगे सर, जेड 8 मीटर पे ही कैलकुलेट करेंगे।
No, you have to calculate it for both the levels, 8 meter and as well as 9 meter, because up to 8 meter you will not be having any pore water pressure. Okay, up to 8 meter, at the level of 8 meter you will be having two pressures for layer 1 and layer 2, but there will not be any pore water pressure as we are getting for this problem.
तो सर एक्सक्यूज मी सर, तो सर उसमें के ए जो है सर के ए 2 कंसीडर करेंगे या के ए 1? जो
if you calculate the
जो
if you calculate the lateral earth pressure for layer 1 you will use ka1, and if you calculate it for layer 2 you have to consider ka2. Are you getting
नहीं
my
सर,
point?
मतलब जैसे सर, मतलब मेरे कहने का मतलब ये था कि जैसे 8 मीटर दिया हुआ है, जो मिडल पोर्शन पे जो दिया हुआ है सर, अगर हमें वाटर टेबल 9 मीटर पे दिया होगा सर, तो हम वहाँ पे K1 कौन सा यूज करेंगे सर? अगर 9 मीटर नहीं कंसीडर करेंगे, 8 मीटर कंसीडर करेंगे तो K2 करेंगे, और वाटर टेबल 9 मीटर पे दिया हुआ है तो सर K1 यूज करेंगे
I
या
think
K2 यूज
the
करेंगे सर?
same question I have addressed in problem 1. Okay, so no
यस सर,
problem.
यस सर।
This is layer 1, this is layer 2, and layer 2 starts from 8 meter, not from 9 meter, because 9 meter is your groundwater table location. Is it clear?
यस सर।
Your layer 2 starts from, because the groundwater table location and the interface between layer 1 and layer 2 is not at the same level. You are having the interface at 8 meter level, however you are having the groundwater table location at 9 meter level. Now up to 8 meter, when you will calculate the passive earth pressure for layer 1, because at 8 meter level you will be having two pressures, one for layer 1, another one for layer 2. So when you will calculate it for layer 1, then you will consider K1. When you calculate it for layer 2, then you will consider K2. However, when you will calculate the pressure at 9 meter, you will be having only one pressure, because this is not the interface. At the interface only you will be having two pressures. You can have two pressures at the interface between two layers. But 9 meter, is it the interface between two layers? No. This is in between layer 2. So therefore you have to use the K2 value only. Na?
यस सर,
Are you getting my point?
यस सर, यस सर।
So 9 meter groundwater table location, this is basically inside the layer 2. So therefore, for the calculation of lateral earth pressure at 9 meter level, you should consider the K2 value. Okay. However, for 8 meter level, you have to calculate two pressures, one for layer 1, another one for layer 2. So when you will calculate the layer 1 value, then you have to consider K1. When you will calculate for layer 2, then you have to consider K2 value. But this is not the case for 9 meter, because 8 meter the interface. At one side you are having layer 2. So just at the top you are having layer 2, and just at the bottom you are having just at the top you are having layer 1, and just at the bottom you are having layer 2 at the same level. However, for 9 meter it's entirely under layer 2. So therefore you should consider K.
ओके सर।
Okay. Okay. Now we'll add the previous components, PA components, and we'll calculate the total lateral force, active force behind the wall after the formation of tension crack. Okay. So just you have to add. So total PA obviously after formation of tension crack. So PA, this should be 13.76 plus 51.40 plus 111 plus 245.
फोर टू 1.16।
Hmm?
421.16।
421.16.
0.16।
Okay. This much kilonewton per meter. So this is the answer for component A. Now we have to calculate the Z bar value as well. That is the line of action of PA from the base of the wall. and for that you have to take the moment above the base. So P A I Z I bar divided by summation of PAI. So summation of PAI already we have calculated 421.16. Now for summation of PAI ZI bar 13.76 multiplied by the corresponding ZI bar, that is 7.69, plus 51.40 multiplied by 5.39 plus 111 multiplied by 1.38 plus 245 multiplied by
2.62, sir.
2.62 or 63. This is the answer for
Okay, sir.
component B. Okay. So I don't know. I have got a slightly different value. So I have calculated earlier this value before the session. So I have got it something 2.75, something like that. So please cross check the values once again. However, the methodology or the approach should remain same. Just you have to take the component wise force and you have to consider the corresponding or calculate the corresponding lever arm from the base, and then you have to take the product, summation of that product divided by the total force, active force, that will give you the lever arm. Okay, so there might be some mistake in the calculation part, so I am requesting all of you, so please cross check these values once again. So maybe there are some mistake during the substitution of the values or inputting the values or in the calculation part. Okay, so it's already 7, so I don't know whether should I move further or should I end this session here. So this is the last problem for today's session. So should I continue or should I end this session here?
ओके बात से कोई सर नहीं, मतलब एंड कर दीजिए सेशन. ठीक है सर, अगले हम कर लेंगे.
Okay. So just before closing this session, just let me read the problem statement and basically let me explain a little bit about the methodology. So this problem is talks about a gravity retaining wall made of concrete, which is designed with the dimensions as shown below. Now we have to basically comment on the design of the wall. Given that the unit weight of concrete is 24 kilonewton per meter cube, adhesion factor for the subsoil is 0.9, and properties of the subsoil it rests on and that of the backfill are listed in the table below. So this is basically a gravity retaining wall. The dimensions are basically shown here, and it is the result of the design process. Okay, so the given gravity retaining wall is basically designed with these dimensions, and these are the backfill conditions and the subsoil conditions. Now what we have to check, we have to basically cross check the design, whether the design is basically done in a correct fashion or not. Now to comment on the design of the wall, we have to check 4 things, as I mentioned at the beginning of this session, that we have to first check that the wall is safe against overturning. So that means we have to calculate the factor of safety against overturning. Okay, then we have to calculate the factor of safety against sliding, and thirdly we have to calculate factor of safety against bearing failure. And this should be the first check, or rather we can put it in this order. So check for no tension condition at the base. And this against overturning, this will be about 2. Okay. Now, what are the recommended values? So against overturning, what are the recommended values? So 1.5 to 2, sliding 1.5 to 2, bearing failure 2.5. And for no tension condition at the base, you should ensure that the eccentricity of the load should be less than the B by 6. Now what is B? B is the width of the base. Here the width of the base is 0.7 plus 0.7 plus 0.3 plus 0.65 that means 3 meter. So 3 by 6, that means 0.5 meter. So the eccentricity should be less than 0.5 meter. Otherwise there will be tension at the base, and if there is tension, so the soil will be separated from the base, and that will not basically resist the overturning or sliding or you have to basically take the appropriate width of the appropriate width that will take also for eccentric condition when the load is basically applied with an eccentricity. So in that case also we have to basically modify the width of the base, that we will see in the next session. Okay. However, tension at the base, that is not desired or that is not recommended. Okay, we should always try to avoid this type of tension at the base, and this tension will arise only when the eccentricity of the loading is greater than B by 6. Okay, so these are the 4 conditions that we should check before commenting on the design of the wall. So if all these conditions are basically satisfied, that is factor of safety against overturning is greater than 1.5, then factor of safety against sliding is greater than 1.5, or the factor of safety against bearing is greater than 2.5, and then the eccentricity of the load is less than B by 6, then the design is safe, design is okay. So in this way we will basically comment on the design of the wall. Okay, so due to time bound we will not be able to solve this problem in detail, so you can basically give a try at your home and let me know what is the result you are getting. Okay, now after this problem there was one homework problem for you, and this problem is taken from GATE examination 2023. So in this problem, a vertical retaining wall with backfill consisting of cohesive frictional soil and a failure plane is developed due to passive earth pressure. The forces acting on the failure wedge are P as the reaction force between the wall and the soil, R as the reaction force on the failure plane, C as the cohesive force along the failure plane, and W as the weight of the failure wedge. Assuming that there is no adhesion between the wall and the wedge, identify the most appropriate force polygon for the wedge. Now as you know that to determine the earth pressure coefficient based on Coulomb's theory, you will be having this kind of polygon of wedge, force polygon for the failing soil wedge. So this is the soil wedge which is basically failing in passive condition. Now in this problem we have to just figure out the correct force polygon. Okay, and that is very crucial before determining the earth pressure, here passive earth pressure. Now how we can determine? So first we have to identify what are the forces involved in this failure mechanism. So first of all, the weight of the wedge, W, wedge in the sense O, A, OAB. This is the failure wedge. Okay. Now weight of this failure wedge OAB, that is basically acting downward. Then the forces are already mentioned in this problem statement. Okay. So we'll consider it one by one. Then what force will come into the picture? The cohesive force. The cohesive force along the failure plane. Okay. So this is the cohesive force. Now, first tell me, I am drawing the cohesive force direction correctly or not? Is it the correct direction in which this cohesive force is basically acting in along the failure plane? Because cohesive force can act in this direction also as well. Now that will depend on the condition which we are considering. So whether we are considering the active condition or the passive condition, depending on that, the direction of this cohesive force will basically change. Why? Because depending on the condition, the movement of this wedge will basically vary. If you consider active condition, then in which direction this wedge will move? And if you consider passive condition, in which direction this wedge will move? So if you consider the passive condition, the wedge will move in the upward direction. Now since the wedge is basically moving in the upward direction, obviously this cohesive force, this is basically a resisting force that will basically try to resist the movement. So therefore this cohesive force should act in the downward direction. But this is the opposite scenario for active condition. For active condition, this cohesive force will act in the upward direction because the wedge is now moving in the downward direction. Okay, so depending on the movement, your cohesive force direction will basically vary. Okay, so two forces we have shown. So the cohesive force and the weight of the failure wedge. Now we'll consider the reaction force on the failure plane. So reaction force on the failure plane, so it will basically act with an angle phi with the normal to the failure plane. So this will be the line of action of the failure plane, a line of action of the reaction R. So R will act at an angle of phi with the normal to the failure plane. Now what is about the passive force? What is the reaction force between the wall and the soil? So the reaction force between the wall and the soil, this will be at an angle delta with the normal to the retaining wall. Okay, so these are the four forces will be acting on this wedge. Now if this statement is not there, suppose there is no addition between the wall and the wedge, it's not mentioned in the problem, then there will be one more force. What is that force? Adhesive cohesive force or adhesive force. Okay, and again this will be in the upward direction. So along the wall face also you will be having some addition, and for that you will be having some this adhesive force which is acting in the upward direction due to the movement of the wedge in the downward direction. But since there is no addition, so C wall, that is 0. However, delta W is not 0. Okay, so if delta W is 0, then this P will be simply horizontal. Okay, so there is wall friction, but there is no addition between the wall and the wedge. So therefore this component will not be there. So we will be having only four forces: the wedge of the weight of the failure wedge, the cohesive force, which is basically acting along the failure plane but in the downward direction, then the reaction on the failure plane, which is basically acting at an angle of phi with the normal to the failure plane, and the reaction to the wall force, which is basically acting at an angle of delta to the with the normal to the wall face. Okay, so these are the four forces. Now with these four forces we can easily determine the force polygon. Now check one by one. If you check one by one, then this option A will not be correct, because here P is basically acting in this direction upward, but this will be in this fashion. Okay, so this will be the fashion. Then this is also not correct, so only C and D are possible options. However, for D, here the cohesive force is basically acting in the upward direction, so that is also not correct. Therefore only option C is basically the correct option. Okay, so if I draw it here, this will be the W in this fashion, and this is the normal, the failure plane. So this is the reaction with an angle phi, and this is the basic force. So this is W acting in the downward direction. This is C in this way. This is R. Okay, so R you can this is R and this is P. So this is the option C is the correct force polygon for the given problem state. So we have already solved this problem, one problem, so there is nothing to do with this problem anymore. So only you can give a try for the problem 5, that is the design check. So for conditions you need to check before commenting on the design of the given gravity retaining wall, and you please have a try at your home and let me know about the difficulties, okay, which you will face in doing so. So this is the end of this session, and we'll again meet on 8th of October at 5 p.m. So have a nice day, and thank you for joining this session.
थैंक यू सर, कॉन्ट्रीब्यूशन। सर ये वीडियो यूट्यूब पे कब तक अपलोड हो जाएगा सर?